Chapter 21, Confidence Intervals. So let's do a little bit of review before we jump into how a confidence interval works. This entire semester we've been dealing with two key ideas, that there's things that are true about the population and there are things that are going to be true about a sample. A population is the complete collection of elements to be studied. This is scores, people, measurements, whatever it is that we're looking at. The sample is a sub-collection or that part of the population. We spent a lot of time talking about how we were going to collect that sample to make sure it was not biased. That is, that we could say it was representative of the overall population. So the sample is usually way smaller than the population. So let's quickly view another example here to see why this distinction is going to be important to us. So say we want to know the average prices of homes in St. Louis County. If we could find the value of every home and take the average, that information would be about the population of homes. So if we have a measurement about the population, it's a parameter. In this example, the population would be all the homes in St. Louis County. And the parameter, that characteristic we were looking at, is the mean or average value. We immediately run into reality, though, and that this is not very feasible, right? It'd be hard to get accurate prices, and we would need a snapshot at a certain moment. So instead, we look at a sample or a subset of the houses to get a feel for what this might be. In this sample, however we pick it, we take an average, and that becomes a statistic. So what we want to do is we want to be able to talk about how does that population compare to the sample? How does the entire collection compare to the part of it, the sample? So samples again are measurement, or the samples give us numerical measurements that relate to part of the population. If we take a measurement about all the homes in St. Louis, we get a measurement about the population. Parameter versus statistic. The parameter is represented by mu, and the statistic is represented by x bar if we're talking about means, right? So mean cost of homes would be mu and x bar. So these symbols are meant to indicate to us which one we're talking about. Are we talking about a parameter or are we talking about a statistic? And so we're finally ready to answer this question. How can we get the statement that the statistic is used to estimate that parameter? It's what we've been working for the entire time. And so I'd like to start us off by playing a simple game. So the first thing I want you to do is to guess what temperature it is outside right now. Don't look it up, don't grab your phone or get on a website, just guess. And so how sure are you that you got it exactly correct? Right? So if you guessed 50 degrees outside, it's exactly 50 degrees. And I just want you to give me a percent chance. Please just participate in this game. I promise it pays off. So write a number down. Probably you didn't give yourself too high a mark. You might have been pretty high, but you gave yourself some chances to be wrong because being exactly correct is difficult. So let's give you some wiggle room. All right, so let's say you're within 2 degrees. So if I guessed 50, I'm now allowed to be correct if it's somewhere between 52 and 48. I'm going to feel more assured that the answer's in there. 5 degrees, even more likely. 15 degrees, I'm even more confident in my answer. So the key here is that as that interval got larger, as you gave me more wiggle room, right? I said, oh, I think it's about 50 degrees. As that about got larger, got spread out, I became more confident that I had guessed the right answer. So there was a greater chance that the parameter temp outside is closer to my guess than farther away, right? I wouldn't have guessed 50 unless I thought it was really close to there. This is described by our normal curve, right? If I center the curve at 50 degrees, I can see that the bulk of my guess, 68%, is within whatever a standard deviation is, right? As I get further away from my guess, it's less likely. So the wiggle room is what this is all about. The confidence interval gives a bound on the wiggle room or the about statement. So if you give a larger sample size, the more sure we are about X bar. If you compare this to our temperature game, have you been outside today? Because if so, that's more information. Have you looked out your window? That's more information. Did you look at the weather report 2 days ago? That's more information. The larger the sample, the more information we have, so the better our guess, the less wiggle room we need. So how certain we are, we use the word confident, we want the interval to be the larger it needs to be. This is a little counterintuitive. You also often hear people use confident as a stand-in for precision, and those are two different things. Keep the temperature game in mind, right? As I increased the wiggle room, I became more confident that the right answer was there. So say we want to form a confidence interval for a population proportion. So what I'm going to do is P is the parameter, the proportion of successes in the population. The sample proportion is P hat. That is, I take some sample size in, P hat is the count of successes, however I want to label that. If the sample size is large enough, the sampling distribution of P hat is approximately normal. That is, my sample could over or undercount P, but it's how likely that is described by a normal curve. The mean of that sampling distribution is the population parameter. We get that from something called the central limit theorem. And the standard deviation of the sampling distribution is given by the formula at the bottom of your page here. So let's put this into action. Suppose 12% of college graduates engaged in binge drinking last year. Well, that would say that the parameter, the answer I'm after, is 12%. But if I grab different samples of students and ask them about this, if I survey about them, I'm going to get a different P hat for every sample that I take. So let's assume we're going to take a sample of size 200. The standard deviation is given by the formula from before, and we get a standard deviation of about 0.023. Well, this curve is going to be centered at 0.12 with the standard deviation of 0.023. What this tells me is that about 95% of all samples of 200 students, in each of those, the proportion of people who engaged in binge drinking is somewhere between 0.07 and 0.17. So this is describing the distribution of p hat. That is where the sample might end up. So from the empirical rule, we get that if I go and take a sample, this is what I'm going to get. But the thing to think about here is that this is kind of happening in reverse of the way it's going to work in the real world. This is happening as kind of a lab setup. Because in reality, we don't know that 12% of college graduates engaged in binge drinking. If we did, why are we doing the study? So all we're going to have at hand is the p hat, but it helps to know what could be happening in the background, right? That is, if we thought it was 12%, this is what the chances of getting certain samples would look like. So now let's see how this works going forward. That is, let's say we want to make a 95% confidence interval for the parameter p. Keep in mind that all we have is p hat at hand. We don't know p. So we're going to substitute in that formula p hats in for p, because that's our guess, right? We took a sample of 200 students. This is our best guess. So let's say I go out and I get my sample, we'll call it sample one, and I get 22 people out of 200 said they had engaged in binge drinking. So my p hat, my estimate for the percent of college students that engaged in binge drinking is 11%. So my confidence interval is 11% plus or minus 0.044. You go out, you take your own sample, and because the samples are random, you're going to get a different answer, likely. So you find that 30 people in your sample said they engaged in binge drinking, so your estimate is 15%. Build your confidence interval, your 95% confidence interval is plus or minus 0.051 from there. So both of us generated our own normal curves from this. Now, how does this relate back to the population curve, right? Because these are two different curves, and we're trying to say that we think the parameter is somewhere in there. Well, for this next picture, I'm going to condense my z-curves. So the arrows, the edge of the arrows is my 95%. The dots represent where they're centered. And how do these compare? Well, this is what they look like in comparison. And now the question is, do they capture the actual P? That is the 12% that we generated. That for this scenario we know, but in the real world we're not going to know. And the idea here is that I take a bunch of samples. If I'm constructing 95% confidence intervals, I'm saying that 95% of them should contain P. So a level C confidence interval for a parameter has two parts then. The interval that is calculated from the data, right? The from this to that, and a level of confidence. That is how sure we are that it's going to capture the right answer. So confidence intervals use the central idea of probability. That is, what if we kept doing this again and again and again? So in particular, right, I have the yellow dot for my sample, the purple dot for your sample, but we're just going to do this once, right? We're not going to repeat the study again and again and again. If we had the resources to take a sample of 200 for myself and a sample of 200 for you, we would just take a sample of 400 people or elements. So the 95% is a statement of probability. That is the probability that the procedure will capture the true parameter, with a really big asterisk there that we'll get to in a little bit, because something is being unsaid there. The interval is only approximately a 95% confidence interval for two reasons. First, the sampling distribution of the sampling proportion p hat isn't exactly normal. The next is that we don't get a standard deviation. In that formula, if you go back to the first time I talked about this, I used P for the standard deviation, and we substituted P hat in to find the standard deviation. So not only are we estimating the center for our curve, we're also estimating the standard deviation. So this is one reason why it's not the same as a 95% chance. We'll see another one in a moment. So if you want to calculate a 95% confidence interval for P, that is the parameter, right? All we have at hand is P hat. It's P hat plus or minus 2 times the standard deviation, where we're substituting in P hat. That 2 comes from our 68, 95, 99.7 rule, right? Go 2 standard deviations up, 2 standard deviations down, you capture 95% of the curve, the area under the curve. So what if we wanted to be 99% confident? Well, for that, we wouldn't want to go 2 standard deviations up or down. We would need a different number. So for any probability C between 0 and 1, there's a number Z star, such that any normal distribution has probability C within it. You're familiar with some of these Z stars. That is, you're familiar with for probability for C, 68, 95, and 99.7, you already know the Z stars of 1, 2, and 3. But if we want to capture 90% of the data, we need to go up 1.64 standard deviations and down 1.64 standard deviations. So we quickly move past that first formula I gave you for a 95% confidence interval, and instead we use this one, because this will give us the formula for any size confidence interval that we want. What you do need is you need that table from the previous slide. We need to know, if you want probability C, we need the corresponding Z star. Note that as that probability got larger, the Z stars got larger. Don't forget the temperature guessing example. If you want to be more confident, you need more wiggle room, right? So using the same sample, because that's all we have the sample data and that's what we know. So we can't just magically, using a formula, be more sure our answer is right. Instead, if you want me to be more sure I got the right answer, you're going to need me to give me more wiggle room. Formula is very similar if we're wanting to do a population mean. So we were focused before on proportions, but say we want to find a population mean. We're going to take a sample, that will be X bar is the statistic, and our formula will look like X bar plus or minus the same Z star from before based on our confidence level C, the probability C that we want, the square root of the sample standard deviation over in our sample size. So let's see an example of this. A medical director for a large company looks at the medical records for 72 executives between 35 and 44. And so she finds that the mean blood pressure for her sample, right, from the 72 she looked at, so this is a statistic, is 126. And again, the standard deviation from her sample is 15.2. So assuming the sample is a random sample of all executives in the company, let's find a 90% confidence interval for mu, that is the unknown blood pressure average for all the executives. So let's take note of our variables here. We know the statistic, that is it's a mean, so we use x bar 126. We know the standard deviation S, that's 15.2. We know that the sample size was 72 because we looked at 72 executives. And I like to make a note to myself here, I'm after mu. That's what I'm trying to get an estimate on. So I don't know what mu is, but that's what I'm trying to guess. So I use my formula here for the population confidence interval for population mean. I substitute in my values. I need to find that Z star. So I go back to my table. According to the statement of the problem, I'm trying to find a 90% confidence level. For a 90% confidence level, that Z star is 1.64. So substitute that in, do the arithmetic, and I will see that the medical director is 90% confident that the true population mean blood pressure for the executives is somewhere between 123 and 129. Keep in mind, this does not say that 90% of people fall, not, I'm sorry, 90% of the executives are somewhere in this range. It says the average is somewhere in this range. Is this the same as having that 90% chance that the correct answer is in that interval? We've already seen that this is just an estimated interval anyways, but we need to circle back to that green asterisk I mentioned earlier, the big assumption that no one's talking about here. And the reality is that the confidence interval's not magic, it's only accounting for random chance. I can't stress this enough. It's only taking into account that the sample was random. And it's really easy for me to show you that this is not the same as a 90% chance of being correct. What if the blood pressure monitor was broken? What if every single measurement it took that day was off by 2? Well, then I would never know that as I calculated the confidence interval. So the unspoken asterisk there, the thing that's not being said when we make a confident statement, when I say I'm 95% confident that it's between this and this, what's not being said, the assumption, the subtext there is that I've done the research, I've conducted the experiment properly. That is, the blood pressure monitor was not broken. So research methods wise, I've done everything I can to ensure that none of these other errors or biases make their way into my study. To further show you this is not the case, note that this is a sampling. Random chance is a sampling error. So there's a whole other category of errors the CI does not take into account. Right? We had a whole list of non-sampling errors, and all of these could still be in effect, and the confidence interval does not account for those. So how do you account for these non-sampling errors? That's all the stuff we covered previously, right? Making sure that we conduct the study properly.